The second half of lesson 6.2 continues with compound interest, and the key word is continues. What we have now is what's called the natural base E. And what this means is if we take our interest formula and kind of simplify it to this model. So as x changes for the number of times it compounds, it also changes your exponent. As x approaches infinity, so it gets bigger and bigger, your answer, oh, there's my cat, your answer will approach a specific number. And that number is, I wanted approaches, not approximates, hang on, okay. We'll get that fixed there. Approaches what's called natural base E. And we could try that. You could plug in 100 to that formula for x. So you would simplify the parenthesis, raise it to 100th power. You could do 1,000, then you could do 10,000. You could even do 1,000,000. Natural base E is the constant that number would approach as x gets bigger and bigger and bigger. And it's approximately 2.71828. 71828. And it actually keeps going from there. And this number helps us with growth and decay models, not only in math, but in science class as well. So you can use this approach in a lot of different situations. But as we bring it back to interest, you'll know you're using base E when it says interest is being compounded continuously. This is different than quarterly or monthly or even daily. When you have a continuous interest formula, the formula is modified from the first page, and we call it the PERT formula. So we're going to say that A equals, and it says PERT, but it's the variables that we use to make happen. P is going to be our original amount again, but now our base, instead of that parenthesis, we're going to default it to base E. And then we raise it to the rate times time power. So P is our original amount. R is the rate, and we change that to a decimal. T is time in years. Well, actually, not necessarily true. We'll just say T is time. There are certain situations where you would use a formula like this, and it is in a year model. So we'll just default this to time. And then A is the new amount. All right, so let's take a look. It says Regina invests $12,600 in an account that earns 3.2% annual interest, but it's compounded continuously. There's our key word. What is the value, just singular, what is the value of her account after 12 years rounded to the nearest penny? Taking a look at our formula, A equals, P stands for our original amount, $12,600. And then our base is E. We're going to have to look for that on our calculators. The rate is 3.2% annual interest, but that means R won't be 3.2, it'll be 0.032. We convert the decimal to a percent in our formula, 0.032. And then time in this case is years, it's 12 years, times 12. Now, on your calculator, you should see a little lowercase letter e. For some of you, there's an LOG button if you have a scientific calculator. That LOG button on the kind of on the top, if you press it, there are a couple of options. There's LOG, there's E, there's 10, and then there's LN, I think. There's a couple of choices. So grab that E button. If you have a graphing calculator, E is going to be on the lower left-hand side, like that column of buttons on the left. You should see an LOG, an LN, and then there should be an E as like a shift function. So hopefully you can all find that button on your calculator. If you can't, and that's okay, if you can't find it, take a picture of your calculator and send it to me, and I will pinpoint exactly where to look to find that button. Now, as we enter this in, you can enter this all in at once. Just make sure that you have a parenthesis around this whole amount if it doesn't already put it there for you. And if you enter this in, after about 12 years, Regina has a nice amount of money, approximately $18,400. $498 to the nearest penny, 63 cents. The continuous formula is pretty easy to work with. Stepping away from interest formulas, the last part of 6.2 will be simply writing exponential models. You'll be given certain information which gives you usually 2 data points. And within those data points, you can write an exponential model following these steps. You want your equation to look like y equals a times b to the x when you're done. Whoa, and just like that, there are 5 steps for you. Go ahead and pause the video, write these steps out, and then press play, and I'll explain what each of these steps mean. In a given word problem, they'll ask you to write an exponential model that describes the data. You should be given 2 points within that word problem. Given those 2 points, write an equation plugging in your values for x and y. Both of the equations would have just letter a and b in them when you're done. Step 2, you'd want to create a fraction with those equations. I know it sounds kind of strange. Create the fraction, and whatever equation has the biggest exponent, put that in the numerator. From there, you'll simplify the left side and the right side of that fraction by applying our exponent rules, and you'll be able to solve for b. Once you get b, we'll plug it back into one of the equations and get a. Once you get once you get a and b, then you can write your equation that would model any situation. All right, let's see how this works. Example 4a. It says Tia knew that the number of emails she sent was growing exponentially. She generated a record of the emails that she sent each year since 2009. What is an exponential model that describes the data? Looking over at the right at her kind of template of a computer, you can see in 2016, she sent 1,400 emails. Down here, I know this number kind of looks like 2016, but it's meant to be 2015. In 2015, she only sent 1,000 emails. So we have 2 data points that we can use to model this exponential function. Thinking about the fact that the years started in 2009, 2015, we're not going to use that number. We'd actually use 6. That's 6 years since 2009. That would be our input, and our output would be the 1,000 emails. And then in 2016, that's 7 years since 2009, she created 1,400 emails. Following our steps, step 1, we want to plug in x and y and create 2 equations. So y equals ab to the x. If I think of my x and my y, that would be 1,000 equals ab to the 6th power. And then that second point, if I think of that as x and y, that would be 1,400 equals a times b to the 7th power. If I can get that in there, there we go. And that's all you do for step 1. Step 2, we use those equations and we create what's called a fraction. And we want the biggest exponent equation in the top part of that fraction. So that would be our second equation. We're going to write 1,400 equals a times b to the 7th. Oops, make that 7 a little bit clearer. Divided by 1,000 equals a b to the 6th. That's step 2. Step 3, we're just going to simplify. 1,400 divided by 1,000 is just 1.4. That was easy. On the right, the a's on the top and bottom would cancel out. The b's, however, if we have b to the 7th divided by b to the 6th, we subtract the exponents. 7 minus 6 is 1. That would give us b to the 1st power, or b. Again, not too bad to solve. Once we know b, we have to plug it back into our equations to figure out what a would equal. Doesn't matter which equation you plug it into. So I will plug it into the second one. Let's see, 1,400 equals a times 1.4 to the 7th power. So I plugged in everything for x, y, and b. To get a by itself, we'll divide by 1.4 to the 7th power. So this is going to be interesting to enter all in at once. 1.4 to the 7th power. That should cancel on the right. And we will approximate this answer. If you can type this in, 1400 divided by 1.4 to the 7th power. Think of order of operations. You may actually want to put all of that in a parenthesis. Plug that into your calculator and let's see what you get. When I entered this in, I got approximately 132.81. We'll go to the nearest hundredth for my A value. Last but not least, our final step, just write our model for any amount of time. The approximate number of emails Tia would send would be y equals our A value, which is 132.81. Our B value, which is our exponential growth factor, is 1.4 to the x. And there's your model. Now it says how many emails will Tia send this year based on her model. This year is 2020. What would we plug in for x? If it's years since 2009, 2020 would be 11 years. So the approximate number of emails would be in the formula y equals 132.81 times 1.4 to the 11th power. Now we wouldn't do an approximate email in decimal form for this. She's not going to send a portion of an email, so round to the nearest whole email. Based on our prediction, what would she get? Type this into your calculator. I got approximately 5,378 for the number of emails she would send. All right, let's try one more. Create an exponential model that passes through those 2 points. Then determine the output when x is 8. We have 2 coordinates. We'll define them as x and y. And we'll follow our 5 steps one more time. Step 1. Create 2 equations plugging in x and y. In that first ordered pair, 16 would equal a times b to the 4th power. In that second equation, we would have 2 equals a times b to the 7th power. Step 2, create a fraction with the biggest exponent in the numerator. That would be that second equation again. 2 equals a times b to the 7th over 16 equals a times b to the 4th. Well, 2 over 16 reduces to 1/8. Again, the a's cancel. Oops, sorry, this is step 3. In the b values, if we take b to the 7th divided by b to the 4th, 7 minus 4 would be b cubed. So now we have a little bit of extra work to figure out what b equals. To get b by itself, we would take the cubed root. And we've worked with this before. We know how to do this. If we take the cubed root of 1, that's just 1. Anybody remember what the cubed root of 8 equals? That would be 2. b equals 1/2. Then what we'll do is we'll plug that into either of our equations, and it really doesn't matter which one we pick. I'll go with the first one this time, something different. If I take 16 equals a times b, which is 1/2, to the 4th power, 16 will equal a times 1 to the 4th power is 1, 2 to the 4th power is 16. Be careful on this step, you guys. To get a by itself, we have to multiply by the reciprocal. The 16s won't cancel out. That's what will work on that right-hand side, but on the left-hand side, 16 times 16 is a whopping 256. Our model then, that would describe this exponential data, would be y equals 256 times 1/2 to the x power. Would this be a growth or decay model? Hopefully you said decay because our b value is between 0 and 1. Last but not least, let's plug in 8 and see what happens. When x equals 8, if we plug in x equals 8, we get 256 times 1/2 to the 8th power. If you enter all of that into your calculator, we get y equals exactly 1. And there's your lesson for 6.2.